Hello everybody, this is Homer White back again with the third installment of Chapter 3 of our course. This is on the relationship between two-factor variables. And in this final installment, we want to study a strange and interesting phenomenon called Simpson's paradox, which can arise when you're studying the relationship between any two types of variables at all, but arises in its simplest and in most easy to understand form when you're studying the relationship between two-factor variables. Make sure that you have the necessary packages loaded into R before you begin. So, what is Simpson's paradox? I think we should take a small example to illustrate it. In the TigerStats package, you'll find a data frame called deffpin. So you want to run the usual commands like data and view in order to get a closer look at it, and you can get some additional information by asking for help, and the documentation on deffpin that's available in TigerStats will appear for you. You can also take a look at the original article. Here is a web link to the article about the deffpin data. It was published by Michael J. Radilay in the American Sociological Review. Now, the research question that Dr. Radilay had in mind was what kinds of racial characteristics of a defendant who's been convicted of a crime where the death penalty is a possible sentence, what kinds of racial characteristics of the defendant might affect that defendant's likelihood of actually receiving the death penalty. One particular specific version of that question is, are black defendants more likely than white defendants to receive the death penalty? Now, this data set is drawn from capital cases where the death penalty was a possibility if the defendant was convicted, in a certain court district in Florida in the mid to late 1970s. When you look at the data frame, every row stands for one of these capital cases. The columns are the variables, and one variable tells you the race of the defendant in that case. Now, in every one of these cases, the defendant was actually convicted. We're not studying the ones where the defendant was acquitted. And so, in every one of these cases, the defendant could either receive the death penalty or not. So there's a variable called death that says whether or not the defendant received the death penalty. So using this data frame, it's possible to study this relationship between race and whether or not one gets the death penalty for this particular region in Florida during the 1970s. So how do we study the relationship between two-factor variables like defendant's race and death? Well, we make a cross table. We think of defendant's race as the explanatory variable in this study, and we think of death, whether or not one got the death penalty, yes or no, as the response variable. So applying our usual formula data input to the crosstabs function, we construct a two-way table, and we'll store it in an object that I call deffd, defendant death or not, I suppose. So here's our two-way table. And of course we want to get some row percents in order to examine the relationship between these two-factor variables. So we take row percents, and here we have the conditional distribution of the outcome, death or not. Given that the defendant was black, here we have the conditional distribution of death, given that the defendant was white. Now we see the two distributions are fairly similar, and in fact, they go a little bit contrary to the way we think things probably should have gone in Florida in the 1970s, back at a time when the civil rights movement was still getting itself into place in some regions in the country. And when most juries were mostly white, you would think that a black defendant would be more likely to get the death penalty in such a region and in such a time than a white defendant. But look at this. The white defendant is actually a little bit more likely than the black defendant to get the death penalty. That's a little strange. Now, things get a little stranger still if you look at the third variable that's available in the data frame. It's a lurking variable in the sense that we haven't considered it yet. This is a factor variable, race of the victim. So just to lay it all out for you here, I've got the structure of deffpin for you, and you do see there are three variables. defendant's race, either black or white, victim's race, black or white, and whether or not the defendant got the death penalty, no or yes. Now, we find that if we take into account the race of the victim, our interpretation of the results is quite fundamentally altered. What we're going to do is to break this data frame down by the values of that lurking variable, victim's race. Vic race is how it's written in the data frame. We can do this by means of the subset function. You can apply subset to a data frame, like DeathPin, and you can pull out a subset of that data frame that satisfies a certain condition that comes after the comma. So, for example, if we want to look at those capital cases where the race of the victim was white, then we would simply put after the comma Vic race equal white in quotes. Now we're going to store the results in DeathPin WV. That's what I call it. So death penalty white victim. Now we'll also construct a little data frame that consists of all of the cases in DeathPin where the victim's race was black. And I'll call that DeathPin BV, DeathPin black victim. And we want to look at each of these data frames separately. So first we'll look at DeathPin WV, the one where the victim is white, and we'll study the relationship between the race of the defendant and death in that data frame. So we make our usual two-way table for the relationship between defendant's race and death, but just for this little data frame, DeathPin WV. And when we ask to print it out, we get our two-way table. Now, when we look at the row percents, we see something rather interesting and surprising. Look at this. 17% of the time, a black defendant would get the death penalty. But for white defendants, only 12% of the time would the white defendant get the death penalty. So when the victim was white, the black defendant was more likely, by about 5%, to get the death penalty. In the overall data, the white defendant was more likely to get the death penalty, but in this subset of the data, where the victim was white, the black defendant was more likely to get the death penalty. So you probably figure that if we look at the other subset, where the victim is black, we're going to have to find that the white defendant is considerably more likely to get the death penalty to make up for the fact that here the black defendant is more likely to get the death penalty. So let's take a look at the other subset. So again, we'll study the relationship between defendant's race and death, but for the subset data frame, DeathPin BV, where the victim is black, we'll get our two-way table, and we'll look at some row percents. And this is very interesting indeed. When the victim was black, and we look at the black defendants, we find that 5% of them got the death penalty when the victim was black. When the victim was black, and we look at the white defendants, we find that none of them got the death penalty. Once again, black defendants were more likely, by about 5%, to get the death penalty than whites were. This is really strange. When the victim was white, the black defendant was more likely to get the death penalty. When the victim was black, the black defendant is more likely to get the death penalty. But at the beginning, we saw in the combined data that the black defendant was less likely to get the death penalty. What's just occurred is an example of what we know of as Simpson's paradox. So Simpson's paradox is what occurs when a relationship between two variables, x and y, reverses its direction when the data are broken down by the values of a third variable, z. Here, think of death race as the x and death as the y. And the original relationship that was that a white defendant was a little bit more likely to get the death penalty. But once we took account of the third variable z, victim's race, broke the data down into the subsets based on the different values of z, we found that in each of those subsets, the relationship was reversed, and the white victim was less likely to get the death penalty in each of those subsets. Now, Simpson's paradox certainly is mathematically possible, After all, we just saw it occur. But could we explain how it occurs in a satisfying way? In order to do that, you have to do some work. I'll suggest a strategy for how you might explain Simpson's paradox. First of all, study how your explanatory variable x relates to that lurking variable z. Next, study how the lurking variable z relates to the response variable y, and then see if you can synthesize the results of these two studies. Let's see how it plays out in this example. We're going to study the relationship between the x and z, the relationship between the defendant's race and the victim's race. So we make a two-way table for defendant's race and victim's race for the overall data death pin. And here it is. Now to get the relationship, we're going to run row percents, and so we take row percents of the table that we have produced. Now what we find is that people tend to kill people of their own race. Look at the black defendants. 62% of black defendants were killing a black person. Only 37.95% of black defendants were killing a white person. Look at the white defendants. About 95% of the time, they were killing a white person, and only a few percent of the time were they killing a black person. When you think about it, these numbers make a lot of sense. In Florida at that time, white people were in the majority, black people were in a minority. So white people, when they went about their business, mostly saw other white people. So it makes sense that they mostly killed other white people. Now, there was a certain amount of segregation still present in Florida at that time. So when black people went about their business, they probably still saw mostly black people, but their being in a majority meant they were surrounded by a sea of white people, and so a good bit of time they would see white people too, and thus they were more likely to kill outside of their race than the white people were. Now let's study the relation between the victim's race and the outcome, the relationship between the lurking variable z and the response variable y. So again, we make a two-way table, this time for victim's race and death. Here's the two-way table, and we look at the row percents. So, what happened when the victim was black? Well, when the victim was black, there was only about a 5% chance for the defendant to get the death penalty. But when the victim was white, there was about a 14% chance for the defendant to get the death penalty. This is saying that your chances of getting the death penalty triple when you kill a white person as compared to when you kill a black person. Again, this makes some sense in a rather sad way. The mostly white juries of that time in Central Florida, I guess they got really angry when a white person was killed and were more likely to impose the death penalty. So now you can put together the results of these two little sub-studies. Regardless of the race of the victim, the white defendants are less likely to get the death penalty. But what's going on is that they hamstring themselves, in a sense, by killing mostly white people. And killing mostly white people is what got juries really mad back in this day. So now we see, in a kind of practical and sociological way, how Simpson's paradox arose in the study. You can see that Simpson's paradox is a pretty deadly thing. If you don't have access to those lurking variables, then you can draw exactly the opposite conclusions from your study from the ones that you should be drawing. Thank you for listening.